Hi everyone and welcome to a new video about noise analysis, and in this video we will discuss the noise analysis of a photodiode amplifier. Now we will also of course discuss an example, so we will carry out the calculation and also do the simulation in SPICE. But before we do that, we will also go through the necessary theory to discuss the example. So our outline of this video is first part 1 is a theory, and we will discuss these topics like a conversion of light to electric signal and a photodiode model, and those topics are shown here. And in part 2 of the video we will discuss an example where we see the numerical values and also verify these using simulation in SPICE. So let's first discuss the photodiode. What we have is a conversion of light to electric signal, which is then voltage or a current. So we have actually a semiconductor device which is used to convert the light into electrical current or voltage. That's actually what it does, the photodiode. Now this is a diagram or a picture of an electric field and also the junction, which is shown here, the P and the N junctions of the photodiode. You can see in between the depletion region, which is formed by placing the P and the N type together. And you can also see the generation of the photons and also here the electron and all the holes parts. The photodiode consists again of the P and N type material. It is a doped semiconductor. It is most of the time a silicon, but it can be also a different semiconductor material. With no bias applied to the photodiode, the free electrons, which you see here, from the N type will combine with the free holes in the P type. So the N type is the source of electrons and the P type is the source of holes. So they will combine if you don't add any voltage across the terminals of this PN junction. And you will then have your depletion region created. That's actually what you have in the steady state condition. Now this depletion region is charged positively in the N-type region, so actually you have the movement of electrons from the N-type to the P-type, and it is negatively charged on the P-type, so we have actually the movement of positive charge, so holes from the P-type to the N-type. So we have actually a separation of charges. Now if you look at this, you have actually a polarization, so you have actually the positive charges and the negative charges in this configuration, and then the electric field will be pointing in the direction from right to left in this diagram also shown here. So the magnitude of this electric field is shown here. So that will also cause the movement of the charges. So the electrons will then move in the opposite direction of the electric field, and the positive charge will be then moving in the same direction of the electric field. So that is actually also what we see here in this diagram. This is already a built-in electric field. Now if you look at the photodiode model, which is shown here as a circuit, we have a number of parameters here. Of course, this is just a model. You can add more, or you can of course also skip one of these elements of the model. Now let's look at the key parameters for our noise analysis. We will of course discuss in the example in the second part of this video. Now we have the junction capacitance, which is shown here. That is actually the capacitance between the two P and N type material, which will be formed by those two elements. We also look at the shunt resistance, which is also a model which will determine the resistance between those two elements. And we have also the dark current, which is actually the current flowing in this material if you don't have any light applied to it. So if you just look at the junction capacitance, which is actually shown here, just the capacitance between these two nodes, we have the shunt resistance, which is actually just a parallel resistance between those two. So we have actually capacitors, junction capacitor, and also the shunt resistance in parallel, and we have the dark current flowing here in this direction. You can see that this is in the reverse direction, which is also the way it is used as a photodiode. We have the other elements here, so we will also go through them. So we have more parameters in the circuit. So what you have is also I sub L, which is the current generated by incident light. So if you don't have any incident light, you won't have this current, so that's just an open circuit. Also you have dark current, so that's actually what you always have, which is sort of a leakage current, but if you don't have, of course, no light. In addition, you have of course the shunt resistance current, so which is of course the current flowing through this shunt resistance. That is also in place here. We have also the output current, which is actually the current which is supplied by your photodiode, which is then flowing in this branch, and in that branch you have also that RS and also the output voltage, which is then of course across this load. What you also have is the diode voltage, which is just the voltage across that diode, which is then the voltage across the PN junction. And we have the output voltage, of course, again, we want that output voltage across a load, and we have the junction capacitor again, and our shunt resistor, and we have the series resistor actually, that is just the model, the connection between this node and to the load. Okay, now that is just a model. Now if you look of course to the photodiode in more detail, you want of course have an optimum transfer of your optical energy to the electrical energy. So we have actually the terminology or the parameter or characteristic, which is called the responsivity versus wavelength of light. Now these are just examples of a photodiode. So you have a number of photodiodes, and you have also in different shapes like this, and you have actually a curve here which will give you the spectral response of your photodiode as a function of the wavelength, and you can see this responsivity will change as a function of the wavelength. Now you can see in this example that the responsivity, which is then amps per watt of photodiode to the light, is affected by the wavelength, and the wavelength is now given in nanometers. You can see also that the responsivity is near zero, almost zero here, between the 400 and 450. So it is actually not really generating any current or any signal in this part of that plot. Now what you have is that it will increase. So as the wavelength will increase, the responsivity will increase and it will reach a maximum. That it is around 775 nanometers, just in this example, not always. Now, if you of course go above, you will increase that wavelength, and you will of course again then have a decreasing responsivity, so you have an optimum value. So if you go beyond that 775 nanometers, you will then decrease your responsivity. Now, there is an optimum wavelength for this photodiode. So most of the photodiodes are actually optimized for a specific frequency and also for a specific wavelength. So that's actually what you have here. So in this frequency range or wavelength, you will have the optimum or the maximum responsivity of your photodiode. Now, different type of photodiodes are designed again to optimize for a specific wavelength or frequency. Now, the diode conducts a current, and that is then the generated current by incident light. So when you have incident light, you will generate current that's called the I sub L. And that is then given by this expression. So you have actually the incident light, which will then create this current, which will then have this responsivity, flux or flux responsivity, times this radiant flux energy. So those two combined in a product will give you that current, and that current is then your generated current by incident light. So if you increase your R sub phi, that is the responsivity, you will of course have more current. That's actually what it is. Okay, now a little bit more about the junction capacitance. It's a very important parameter also for our noise analysis shortly. Smaller junction capacitance will lead to lower output noise. So if you have a small capacitance, junction capacitance, you will have low output noise. If you increase your junction capacitance, you will then increase also your output noise. That's actually what it is in this very small statement, increasing the reverse bias, because the photodiode is operating in the reverse bias, that's the VR, will decrease then your junction capacitance, which is then of course good in terms of noise. So that is then given by this expression. So junction capacitance, C sub J, is then given by this formula, which is then zero bias junction capacitor given by this. So that is actually the junction capacitor you always have without any reverse bias, and you have that square root of 1 plus that reverse bias divided by a built-in potential, which is then a specific parameter linked to that material you are using for your photodiode. So again, junction capacitance, this is then your junction capacitance at zero bias, so you have no bias applied. And VR is your reverse bias voltage in volts, and this is the built-in potential of your photodiode junction. And it will of course change if you have a different photodiode. Now, what you also have is the IV characteristics, so the volts versus the current. So what we have is several plots here. As you can see, actually, if you increase your light, so increasing the light level or your incident light, you will see that this curve, the blue curve, will shift to the green and also to the brown side, or the dark red. So you can see actually you will generate more current in this form. Actually the reverse part, because this is the interesting part for us, because we are operating for the photodiode in the reverse characteristics or reverse direction. So with no light applied to the dark, the photodiode acts actually as a conventional rectifier. Just look at the blue line, which is for a case where you have almost no incident light. This is just a very simple signal diode, which will then conduct at around 0.7 volts, and then will go exponentially up in the current as you increase the voltage. And in this case, it is approximately 0 for your current. So that's actually the conventional rectifier. Now, increasing the applied light will of course shift that curve in this direction to down direction, and you will then have more light current. Okay, that's actually what we already said. So we can then continue now the circuit, the transimpedance amplifier, which is just one of the amplifier topologies we can use to amplify our signal, what we have from our photodiode. So the circuit is then like this. So we have the photodiode, again in the reverse direction. You can see the photodiode. It can have a bias here, but it can also have a ground. It can also have a reference at one of the inputs of your operational amplifier. Now the operational amplifier is shown here, which will then of course has the current as an input. The feedback is formed by the capacitor and the resistors. This will be discussed shortly in great detail. And we have of course the output, which is then a volt, so it is actually the voltage. So you have the input is current, the output voltage, so the volts divided by the amps, that is actually the impedance, just using Ohm's law. That's why we call it transimpedance amplifier. So that's a circuit. What you see is that it converts electric current to voltage. So that's actually the transimpedance amplifier, and it is also called for short TIA. Now output voltage is calculated by multiplying the input current from the photodiode with a feedback resistor. Of course, the capacitor will also have some effect, and it will also have some frequency dependency, but if you look only at DC operation, then the RF, the feedback resistor, will be the determining part for your gain, and that was then the transimpedance gain. Now the bandwidth of the circuit is then is actually separated in two parts, two important parts, and that are the noise bandwidth and also the noise gain. Those two will actually determine your bandwidth for this circuit. What you also have is your signal bandwidth, which is then of course the cutoff frequency that is limited by this resistor feedback and also the capacitor in the feedback. So those two will determine your cutoff frequency and also your noise bandwidth, because the cutoff frequency is exactly equal to the signal bandwidth for this circuit, and that is also linked to that noise bandwidth in this circuit. So if I have a cutoff frequency given by this expression, just the low pass filter operation here for this product, for the RF and RCF, then you have actually just from this you can go to the noise bandwidth. Okay, the noise model for our transimpedance amplifier. Next we will discuss the noise model of the transimpedance amplifier, because that is the circuit we are using to amplify the photodiode signal into an electric voltage at the output. So we have this model for our transimpedance amplifier. You can see the photodiode model with the necessary elements like the junction, capacitance, and also the noise current source, and also the shunt resistance actually of that photodiode. What you also have is that the resistor in the feedback, RF, and also the associated noise voltage source, and we have the feedback capacitor, of course, that is noiseless in terms of the for the capacitor, because that is a reactive element. We also have the op-amp model, which is then the noise model of the op-amp. We have the op-amp capacitor at the input. We have its own noise voltage source and also the noise current source of the op-amp. So this part is just for the op-amp, this part is for the resistor, and this part is for the photodiode. And again, capacitor doesn't generate noise. So we have three subsections: photodiode, op-amp, and also the resistor. And those, each subsection will then be modeled as a separate, using separate noise sources. Now all three subsections will be then combined to compute a total output noise voltage. And noise will be, of course, determined by the capacitor at the input, and also the capacitor in the feedback, the shunt resistor, and also the feedback resistor. Those four elements will determine the noise at the output. And that will give you then the shape also of the noise gain. Now the input capacitance Cin is actually the sum of the junction capacitance and also the capacitance of that op-amp, which is then COPA. Okay, now the photodiode and the op-amp noise current sources. Let's go through that step by step. The terminal noise current input referred is as follows. The terminal noise current spectral density, you have that for the photodiode due to that shunt resistance. So this will also generate a terminal noise current. And that's then given by this formula again, for kT, K for the Boltzmann constant, T for the temperature in kelvins, and this is the resistor value in this model. And also shown here. You have also the shot noise sources, and again input referred. Shot noise is then proportional to the DC current. So if you have DC current flow, you will have a shot noise. So that is only present in DC. We have two types of shot noise in the photodiode, which is then the shot noise due to the current flow if you have light applied to it. And you have also, that is then given by this expression, which is then ISL, the square root of 2Q times that current, and the Q is here the elementary charge of the electron, and the DC current, which is flowing in this form when you have light. And you have also shot noise due to the current flow when there is no light, which is in the dark current. Again, a similar expression, again 2Q times that dark current. Now if you combine these three noise current sources, two shot noise and also one terminal noise, that will give you the total photodiode noise current, which is then again added together using root sum of squares. So you square each element, add them up, and then take the square root of the sum. Okay, the total input noise current, which is then a total photodiode noise current and also the output, op-amp noise current together, that is then given by this expression, which is then of course the photodiode noise current and also the noise current source by the op-amp together, and those two will be then again combined together using root sum of squares. So you will square each of them, add them up, and then take the square root. The total output noise voltage due to the noise current source of the photodiode and the op-amp can be calculated using this, which is just Ohm's law. You just multiply this by the resistor, feedback resistor, you will have then your output noise voltage due to the input noise current source and also the RF, which is the feedback resistor. So this is just one contribution. Now the total output RMS noise voltage due to the noise current source of the photodiode and also the op-amp will be then given by this expression. So once you have this, which is then the spectral density, then you have the RMS value if you multiply that by the square root of the noise bandwidth of your circuit. That is of course what we in the final form want to calculate. Now the terminal noise voltage, that is the feedback resistor, output referred, can be calculated using the formula which is then actually shown here. So this is again the very familiar formula for calculating the RMS noise voltage of a resistor, which is the 4kT resistor value times that noise bandwidth. Noise to the op-amp noise voltage source, which is then due to this one, can be calculated using the model shown here. So we actually focus only on the op-amp noise voltage source here. You also use the input capacitors, which is the junction capacitor, and also the op-amp capacitor together, which is then Cin, and you have also the RF and also the CF. Now the final contribution to the output noise is the intrinsic noise voltage source of the op-amp itself. So the noise gain is the gain seen, that is actually definition, seen from the non-inverting amplifier, non-inverting input to the output. That is very important. So the capacitance CF and also the Cin will cause a peak in the noise gain curve that will significantly affect the output noise voltage. So the noise gain will be determined actually by these two capacitors, not just the RF only. So the op-amp input capacitance, COPA, is actually also composed of the differential mode input capacitance and also the common mode input capacitance, and that is also actually available in datasheet of the op-amp. So that can be determined from the datasheet. We will see that numerically in our example. So also about the noise gain, if you use Kirchhoff current law, so KCL, on the inverting input, you can determine analytically what your noise gain will be, and that will be then in this form, because you have now three current paths. So you have actually the current in this Cin, you have the current flowing in this RF, and you have also the current flowing in the CF. There is no current flowing in the op-amp because the op-amp has no current flow in it, because the input impedance of the op-amp is considered as very large, or in this ideal case an open circuit. So you can see then the following. You can say, okay, this voltage is also there due to that negative feedback. That voltage over that reactance, which is then this one, is the current. And again, this voltage minus that voltage at the output divided by the RF, which is then the current flow in this. And again, in symbol form, this voltage over minus that voltage over the reactance of this capacitor shown here is then equal to 0. That's just Kirchhoff current law at this inverting node. Now, if you simplify this, and then you solve actually for the noise gain in S domain, so it's actually the lot loss domain. What is the noise gain? Noise gain is the output noise divided by the input noise, which is then of course the noise voltage source of the op-amp. You will have this expression. What you see is you have a pole, which is given by this expression. So if you equate this to 0, and you have also the 0, which is given by the numerator of this expression by equating this numerator to 0. So you have one 0 frequency and one pole frequency. The 0 frequency is given by this expression, and the pole frequency is that which is then the cutoff frequency also is given by this expression. So you will of course need to use this in the noise analysis in our example. Okay. Very important topic is, or part of this discussion, is the frequency parameters in our circuit. So we have, in addition to the zero frequency and also the pole frequency or the cutoff frequency, we have other frequency parameters to carry out the noise analysis. Now, the location of the relevant frequency parameters can be seen in the body plot for open loop gain and also the noise gain. Let's look at it in more detail. This is just the open loop gain plot, this dark red line, which you can see also in the datasheet. And this little bit light green part, which is then given is the noise gain curve, is determined by your circuit itself. And you have actually a part which will then stay a constant, that is then determined by the capacitor at the input and also the feedback capacitor. That is the plot, and you have then an intersection and also other parts which will then increase and also settle down, and those are all given here with specific names for the frequency. Those are the frequency parameters. So the cutoff frequency, again, this is determined by the feedback resistor, RF, and also the feedback capacitor. Again, this formula. We have the zero frequency determined by the feedback resistor and also the input capacitor, which is then given by this formula. Again, of course, we have also the feedback capacitor in it. Now, the 1/f noise and the broadband noise intersection frequency, which is actually this part, is given by this expression. So we need the normalized voltage in a voltage density and also the broadband noise voltage, and you will need to square that. You will have then this value, which is then called the intersection frequency for the 1/f noise and the broadband noise voltage. We also have the noise gain and the open loop gain intersection frequency. So this is actually this one. So I actually pointed for this one, which is not correct. This is just another frequency. So we have actually this, and this is then for this part, and you can see that this is actually determined by the ratio of the capacitors times the unit gain frequency, which is actually shown here. That is the frequency where the gain or open loop gain is 1 or 0 dB. Now, in addition, the unit gain frequency just from the datasheet of the op-amp, and also we have the lower band frequency, which will be used in the 1/f noise analysis. So, which is then given by f sub L, which is usually taking as 0.1 Hertz. But this will be clear when we work out the examples in great detail. Okay, SPICE simulations. This is of course very important, because to able to do the SPICE simulations, you need to adjust your SPICE circuit to determine the open loop gain and also the noise gain. And this is also important for the analysis and also the calculations for our noise. So this circuit is what we use to determine the noise gain and also the open loop gain and also other elements in it. But you see again the capacitor and also the resistor and the feedback. You have your diode here, which is just only the junction capacitor, which is just sufficient for the analysis in noise. And what you have is the generated voltage source here, the capacitor and also the inductor and also the current here. This current will measure the current actually which will be flowing through this parallel combination. This is the input voltage will be then also measured, and also the output current will be measured and also the output voltage. So how is it defined? You can see the output open loop gain is defined actually as the V out over V in, which is then open loop means actually that DC what will actually happen. That is actually the value what we have here. Of course, as a function of the frequency, this will of course change. Now, noise gain is then defined as the input here V in over V diode. So what we want is actually what this node is, the voltage at this node divided by the V diode. That is actually the noise gain. Transimpedance gain or the signal gain is of course the output voltage divided by the input current, and input current is actually also the same as I out, because this current here flows through these two branches and come back and joins again here, makes it I out. So you will actually have the V out over I out. That is your signal gain. So we have these three elements, and using the simulator you can then use post-processing and then generate these 3 plots. Okay. For the output RMS noise voltage, due to the op-amp noise voltage sources, that is a very important part, because you have the curve which will then have several regions divided in 5 regions, R1 up to R5. So R1, R2, R3, R4 and R5. And I will go step by step, and you can see also the frequency parameters we have just discussed. We have the FL, which is then the lower bound for our 1 over F noise region. This is the intersection between the 1 over F noise and the broadband region. This is the zero frequency, which will make actually the output noise voltage increase. You have the cutoff frequency, which will then settle down actually that part again, and we have the intersection frequency between the open loop gain and also the noise gain, and you have then the unity gain frequency, which will be the frequency where the open loop gain is 1 or 0 dB. Now, for each region, we can then set up an expression for the output referred noise voltage. That will then be done step by step, and you can then combine the separate effects to get the total output noise. So, this is again our plot. You can see the different frequency parts and also the noise gain and open loop gain, and also the part which will then give you the gain at the constant value for a noise gain. Okay, the region 1, the R1, is determined by this expression, given by this expression also, is also shown here, which is then the broadband noise volt spectral density times the square root of that frequency here. We need to determine also the ln of that frequency divided by that frequency in that lower bound. So you can then select this as 0.1, for example, from your datasheet. For region 2, that's actually for this region, you need to actually use just the broadband part, which is then this frequency minus that frequency, and then square root of that one times the noise voltage spectral density. This is actually very straightforward formula. For region 3, we can again have a similar formula as this one, but it is now increasing, so the formula is a little different. I'm not going to drive it, it is just what we use it, and you have then this formula. You can see again the cutoff frequency and also the zero frequency is in this expression. In region 4, which is then in this pink part, is then given by this expression. In that part, the noise gain of your circuit will be in place, and also the parts between the intersection frequency, between the open loop gain and also noise gain, and also the cutoff frequency is in here. Now the final one, region 5, is then given by this expression, which is then a unity gain frequency and also the intersection frequency, and also again the broadband noise voltage spectral density. So these are the formulas to determine the noise contribution for each part, and the frequencies we need to determine using the formulas in the frequency parameter discussion we have discussed earlier. Now the total RMS output noise voltage due to the op-amp noise voltage source is then given by the root sum of squares formula. So you actually take the square of each element here, each parameter, add them up, and then take the square root, and that will be then the contribution of the noise voltage sources due to the op-amp noise voltage source. So that is what we have as one of the parts for our noise analysis. Now the total output RMS noise voltage, how is that determined? That is then, first one is the output RMS noise voltage due to that feedback resistor, just a thermal noise. We have already discussed this. And we have of course also the output RMS noise voltage due to the input noise current sources. Those are also given, so you have the feedback resistors, and then times that square root of that square elements for each part. So this is actually the shunt resistor current, which this is the dark current shot noise, this is the light. So actually when you have a light incident light, the shot noise due to that one, and this is just the noise current of the op-amp itself, and add them up in the root sum of squares, and you need to of course multiply by the square root of the noise bandwidth. These are all in RMS value. So you have also the RMS noise voltage due to the input noise voltage sources of the op-amp. Now, we have already discussed this. This is the expression, and we have all seen the separate elements in it. Now, if you want to combine this, of course, and again in this expression, what you do is a total output RMS noise voltage is then square this and square that, add them up, and then take the square root. That is just actually the final output noise voltage. Okay, stability in transimpedance amplifier, really important parameter. Some important notes before we move on. Stability of the transimpedance amplifier is an important concern. Understanding the noise gain curve will give you a lot of insight of the amplifier stability. Now, we have large capacitance can be happening on the output of an amplifier, tends to make this circuit and also the system unstable. We already discussed this, and we already said that lower capacitance will make your system or your circuit stable. So if you have a large capacitance, be careful about stability. Now, because photodiodes have large junction capacitances, we have definitely stability issues, so we need to consider that in great detail. Now, photodiode or photo amplifier without a feedback capacitor, if you have that, so photodiode without a feedback capacitor is in fact already an inherent differentiator. So what you have is that it will not be stable because of the rate of closure between the feedback resistor or feedback network, which is the noise gain, and the open loop gain curve, which is then equal to 40 dBs. We can see that in great detail shortly. Now, from stability theory, if you have a system, and for any system actually, which has a rate of closure, so the ROC, larger than 20 dB, it will not be stable. In our case, it is 40 dB, so we will see why is it 40 dB and why is that then unstable. So you can see again the plot here. If you have this open loop gain plot, and this is your noise gain plot without the feedback resistor, so you actually don't have that settling. This is the intersection between this dark red line and this green line. You can see actually that this rate of closure here is 40 dB per decade. Why? Because this is decreasing by this is actually decreasing, the slope is here minus 20 dB per decade. This is increasing, sort of a differentiator action, 20 dB per decade. So actually this part has a rate of closure of 40 dB per decade. So again, noise gain continuously increasing by 20 dBs per decade after the zero frequency, so the zero frequency is around here, and there is no pole to actually settle this down, which will of course be caused by the feedback capacitor and also the feedback resistor. So the rate of closure is then defined as a difference between the slope of the open loop gain and also the noise gain, and where they intersect. So in this case it is 40 dBs because this is the difference between them is 40 dBs. So 20 dBs minus 20 dBs, you will have 40 dBs per decade, which is of course then much larger than the 20 dBs which is maximum allowed to have your stability. So to ensure stability, what it actually means is if you want to have a rate of closure less than 20 dBs, then this line actually must already go flat when you intersect your open loop gain curve. So for stabilizing the photodiode amplifier, you can make it like this. So the noise gain will then catch up due to that zero, and then it needs to level off by that pole due to that feedback capacitor and also the feedback resistor. So reduce the rate of closure between the noise gain and also the open loop gain to 20 dBs per decade or less. You can also by introducing a pole. That is of course the feedback capacitor. The noise gain curve flattens out before it intersects the open loop gain curve. So of course you can shift this to the left side to have more margin, more safety. Of course there's a warning here. A small change in the capacitor or the open loop gain can cause of course the amplifier to become unstable. So if you just take it at the edge, you can of course have a very small margin, so place it on the left side will give you more margin. Okay. Okay, the rule of thumb here is, what engineers most of the time use, is the following. The intersection here, which is then Fi, is selected as a frequency which is then 0.5 to 1 decade lower for more good design margin. So if you determine this frequency, it will be taking 1 decade smaller or 0.5 decades smaller than that one. So let's say this is then 100 or 200 kilohertz. You can place it at 20 kilohertz, just 1 decade lower, then you will have good design margin. Okay, that's for the stability of the transimpedance amplifier, really important topic. Okay, let's go to a very short example calculation and what the effect is of a feedback capacitor. So if you have a situation where we have a photodiode amplifier with an op-amp and it has a unity gain frequency of 150 megahertz. The input capacitor or capacitance of your circuit is 70 picofarads and the feedback resistor is 1 mega ohms. Okay, the question here is the following. What is the required feedback capacitor in order to make this photodiode circuit stable? Because in this case, without the feedback capacitor, this circuit is definitely unstable. So what we can do is the following, where there is a solution, and also we will now also introduce the formulas to do that in an exact form and also in simplified form. First, the simplified form. The minimum required feedback capacitance is given by this expression, Cin, which is what we have, and also the RF, and this is the unity gain frequency, and this will give you then your feedback capacitor, minimum required. And if you now substitute the values in here, 1 mega ohms, 150 megahertz, you will have here 272.5 femtofarads. That's actually what you really need minimum to have a stable circuit. A more exact formula to calculate that C capacitor, feedback capacitor, is this. And if you now also substitute the required values, you will get 273.1 femtofarads. What you see is actually that is not really that much different. So in most cases, the simplified formula will do the job. What you need to understand here is increasing the feedback capacitance beyond the minimum required value will ensure, of course, stability design margin. So if you have calculated this, let's say take 300 femtofarad, maybe a little bit larger, that will give you, of course, some margin, some safety. That's just in a very simplified form and exact form how you can determine your required capacitor in the feedback in your transimpedance amplifier. Okay, let's now look at an example with the complete circuit. We have the following situation. This is our circuit, and this is just used to be able to do that noise analysis. So this is not doing anything, it's not used. We have the capacitor in the feedback, the resistor in the feedback, which is 100 kilo ohms. We have the capacitor in the feedback, which is 4 picofarads, and we have the operational amplifier OPA 827. And it is now a power supply of -15 and +15. And we have the photodiode, which is then given here by the C diode, which has a value of 70 picofarads. This will be discussed shortly. What we want is the calculation of the total RMS output noise voltage at the output, and a part of the datasheet of the photodiode and also the op-amp are also shown below. So let's first look at the photodiode. This is the datasheet from the photodiode. What you see is actually the following. You can see that the dark current of 2 nanoamps, this is just DC current. We can see also that the junction capacitor is typically 70 picofarads. That's actually what we have there in our simulation. So the junction capacitance, 70 picofarads. Which also have as the shunt resistance is 150 mega ohms. So that is also what we have. So those are the elements we will use in our calculations. And for our simulations, we only use the capacitor, and it will just do the job. And of course we will have some differences, but that's also what we just take as an error, but we'll see how much that error is. Okay, this is the the data from the datasheet of the operational amplifier OPA 827. You can see the following information from this datasheet. You can see that the gain bandwidth product here is 22 megahertz. You can see also that the broadband noise voltage density here is 3.8 nanovolts per root hertz. And you can also see that the input current noise current density is 2.2 femtoamps per root hertz. What you also see in this plot on the right side is this is for the input noise voltage density versus frequency. This part is the 1/f noise part, and this is the part where we have the broadband noise part. So we have here this part, which is 60 nanovolts per root hertz at 0.1 hertz. It's again that FL, which is the lower band frequency. So that is the 1/f noise voltage density for our operational amplifier, which is then 60 nanovolts per root hertz. Now the 1/f noise current density, there is no current density, 1/f noise current density for this op-amp, which is just 0. So these are the important parameters for our op-amp and also for our photodiode to able to do that noise analysis. Okay, let's look at the circuit performance. First, bandwidth. The bandwidth will be determined, of course, by the feedback elements, the CF and the RF, and the cutoff frequency, feedback capacitor, and also the feedback resistor, which is then given by this formula. Now, signal bandwidth is equal to the cutoff frequency in this case. So if you just substitute the values, I will get approximately 398 kilohertz, or approximately 400 kilohertz. Now, the closed-loop noise bandwidth, assuming a first-order circuit, assuming that we have then a break-wall conversion factor of pi over 2, I will just multiply this with the signal bandwidth or the cutoff frequency. I will have then this 625 kilohertz. This is what we will use in the noise calculations and not this frequency. Okay, now frequency parameters again. We will of course summarize this here using the formulas we have discussed earlier in the theory part. You know, the gain frequency from our data was 22 megahertz from our op-amp. The cutoff frequency just calculated was 398 kilohertz, and the zero frequency, which is then determined by the feedback resistor and also the feedback capacitor and also the input capacitors of the circuit. So what we have is then the following. This is what we have, and if you now just look at the input capacitance of this circuit, which is then the junction capacitor and also the op-amp capacitor. An op-amp capacitor is a sum of the common mode input capacitor and the differential mode input capacitor. Now, so the op-amp is then this, the combination of the common mode and the differential mode input capacitances. If I look at the datasheet, I will see this parallel combination for the differential and parallel combination for the common mode. Now, this means actually I have 10 to the power 13 ohms in parallel with 9 picofarads for the differential mode. The same is also for the common mode, so I will have 9 picofarads for the differential mode input capacitor, and the common mode input capacitor is also 9 picofarads. So I can say from the datasheet, I can say this is 9, this is also 9, so combined is 18 picofarads. So the input capacitor will be then 70 picofarads by your junction capacitor of the photodiode. I have 18 picofarads due to that operational amplifier. I have then 88 picofarads in total. Okay, then the zero frequency can be calculated now using the values here, the RF we have now, and also the C-in and also the CF, and this is then 17.3 kilohertz. Okay, now we will of course select a lower bound frequency for 1/f noise region calculation, and this is usually taking a 0.1 hertz. So we already said that, and we also listed here. The 1/f noise and also the broadband noise intersection frequency is given by this expression, and we know this from the datasheet and also this from the datasheet. Now this can be calculated from the datasheet using this formula here. This is 60 nanovolts per root hertz. We already discussed this, and this is then 0.1 hertz for the lower bound frequency. Now if you now do the math here, you will get 18.97 nanovolts RMS. If I now also substitute in here and also the value from the datasheet, I will have now the following expression, and it will give me 24.92 Hertz. That is for the next one. Okay, the noise gain and the open loop gain detection frequency, Fi, is given by this expression, and I will of course use again my feedback capacitor and also my Cin and also the unit gain frequency, and I will have this value, which is then 957 kilohertz. Okay, this is then for now for the frequency parameters. Okay, the terminal noise voltage from the feedback resistor. Let's look at this again using the Junction noise or terminal noise formula, and the bandwidth is then limited by the signal bandwidth, of course the noise bandwidth, because we use the first order circuit approximation and we use the Brickwell conversion factor. Then we have the following situation. We have the 4kT for Boltzmann's constant, the temperature, the value of your feedback resistor, this is the noise bandwidth, and this is then our noise voltage contribution due to that feedback resistor. So it is 32.17 microvolts RMS. Okay, that's just for the resistor. Now we have the noise voltage due to the op-amp noise current source and also the photodiode noise current source. Now, photodiode noise current source is the RMS value of the three different noise sources. We already said that. This is the shunt resistor, will generate some noise current, short noise due to the dark current, and also the short noise due to the light current, which is then due to the incident light. Okay, now if you now combine them together, of course normally we consider the terminal noise of the resistor to be a voltage noise, but in this case it is better to have a noise current. Okay, let's look at the terminal noise current spectral density of the photodiode and the shunt resistors, which is then this expression, and if you now substitute the values in here, you will get 10.5 femtoamps per root hertz. Now for the short noise sources, again in a similar form, this is we have again two types. Short noise due to the dark current, which is then this expression. This is the value, and for the short noise due to the light, you have again similar expression, because there's no light and we have a 0. So that's actually what we take actually for this example. So if you have light, you will have of course also the incident current here, IL. Okay, now total photodiode noise current density, which is then given by this, and of course I have only the shunt and also dark current noise current sources, and this is then the result, 27.4 femtoamps per root hertz. Total noise current density, just the current density, so that is the total input noise current from the photodiode with the input noise current of the op-amp will generate the total output noise current spectral density. Okay, that will flow through the resistor in the feedback, and that will generate or form output RMS noise voltage just using Ohm's law. Okay, the input noise current of the op-amp was 2.2 femtoamps per root hertz, just datasheet. Now total output, the total noise current spectral density then is given by this expression. We already calculated this, 27.4 femtoamps per root hertz. This is from the datasheet, and I have then 27.5 femtoamps per root hertz. Which you see actually is that this is still dominating that part from the op-amp, is not really that important for this case. So the total output noise voltage spectral density due to the noise current source of the op-amp and also the photodiode is then given by this. Again, using Ohm's law, this times the resistor. In the feedback you will have 2.75 nanovolts per root hertz. Okay, the total RMS output noise voltage due to the noise current source of the op-amp and also the photodiode is then given by this. This is the RMS value. You multiply this by the noise bandwidth, the square root of the noise bandwidth, and you will get 2.173 microvolts RMS. That is the contribution by the noise current sources at the output. Okay, the final one is the noise voltage due to the op-amp noise voltage sources, and those are of course again the 5 regions here. We have now again the R1 up to R5. And for each region we have the contribution, and we have discussed this, and we have now the important frequencies determined in the previous discussion, and these are now summarized here. Now what we have is the region 1. Now if you now just substitute in this formula the required values from here and also from this broadband noise voltage spectral density as 3.8 nanovolts per root hertz, you will get 44.57 nanovolts RMS. Now if you do that similarly for the R2 using this formula, you will get this result for R3, this result for R4 and R5. So for these 5 regions you will have these results using this value from the frequency parameters. Okay, now if I now combine these to get a total RMS output noise voltage due to op-amp noise voltage sources, again using the root sum of squares formula, just substitute the values, I will get 112.2 microvolts RMS. That's the contribution just by the op-amp noise voltage sources. So we combine the separate output revert noise voltages using root sum of squares. This is what we had for the contribution due to the noise current source at the input and also the feedback resistor. This is what we had. This is just by the thermal noise voltage due to the feedback resistor RF only, and this was the noise contribution by the noise voltage sources of the op-amp only. Now if you combine them together, you will have then, using root sum of squares, this expression. If I now substitute that, these 3 values, I will have 116.7 microvolts RMS. Again, you can see this is the dominant part actually in this circuit. So major contributor or major contributor for the total output noise voltage is the noise to the op-amp noise voltage source. Now let's also look at the signal-to-noise ratio, SNR, which is a very important parameter. And signal-to-noise ratio is actually a measure that compares the desired signal level to the noise level. And a more precise definition is actually the ratio between the signal power and the noise power, and it's often expressed in decibels. So a ratio higher than 1 or greater than 0 dB indicates more signal than noise, and if you have of course a ratio which is then between 0 and 1, which means actually a negative dBs, that indicates you have more noise than signal, which is of course not what we want. So we will actually want to have the SNR to be as large as possible. Now for this circuit, the SNR at the output for a specific frequency can be calculated using this formula. You need then the total output noise voltage in RMS. Now we have this, and if I now substitute that in here, I will have 78.7 dBs, and we will also verify this shortly. Okay, let's now look at the simulation result and to output noise voltage spectral density first. This is the plot what we have for this circuit using this very simplified model for our photodiode, and this is the feedback capacitor and the feedback resistor and also our op-amp. What you see is it has a value here for very low frequency, 0.1 Hertz, and this is the part what we call the 1/f noise region. This is then the part which is then the broadband region, and we have also the gain peaking here, and that all goes down to approximately 0 when the frequency goes to approximately 1 gigahertz. So in summary we can see the following: frequency is dependent, which is in this part, 1/f noise. Frequency is independent in this part, which is then the broadband or white noise region. We have gain peaking here. That is actually due to the feedback capacitor. So if you change that, increase that, you can decrease this peak. So that's also all determined by this feedback capacitor. And the output noise goes to 0 due to the bandwidth limiting of your circuit. That's actually due to the cutoff frequency of your circuit here. Okay, now the total RMS noise voltage, that's actually very important because we have calculated that. Now we will check that. This is again our circuit, and what you see is the calculation. Let's first again remember that the calculation was 116.7 microvolts RMS, again with this very simplified model for our photodiode, just a capacitor of 70 picofarads. What you see here is I've just given here 3 labels. This is of course the value what we have calculated, but what you see is at this frequency 100 megahertz, you can see it is 118.12 microvolts RMS. If I of course go to 1 gigahertz, this will go to approximately 133.05 microvolts RMS, and will maybe also a little bit increase, but it will then settle down at some value. But you can see this value at around 100 megahertz is already very close to that one. You might ask why I take this value and not that one or not that one. Now the cutoff frequency of our circuit was in the calculation was approximately 400 kilohertz. So if I go 1 decade above, it will be 4 megahertz. So if I go even another decade above, it will be 40 megahertz. So if I do that, just as the integration bandwidth discussion, we have done this also in the previous videos, I can select this frequency and then compare that to the calculation here. So the simulated value here is 118.12 microvolts RMS, and that is at that frequency. Of course, if you want to look at a lower frequency, you will have some differences. That is very normal, actually not surprising, because our model is not really that complicated. So if you make your model complicated, you will have of course also a more accurate result from the simulation, and that will match the calculations nicely. So in this case, even though we have some differences from the simulation and the calculations, using the very simplified analysis we have done here, the result is very nice. Okay, let's also look at the signal-to-noise ratio. This is the plot that we have again. What you see, the calculation was using this formula given here. This is actually what we had, using of course, and then using the total output noise voltage. But the simulated value was 77.5 dBs and we had 78.7 dB. So it is a little bit larger in our case. That is due to the more noise actually at the output than we have calculated. Because this was what we have calculated, and it was actually in the plot in the previous slide. You were seeing actually it was going to 132 microvolts RMS. So that is a little bit more. That also will decrease your SNR. Okay. This is about that photodiode analysis. First part was a theory, and the second part was the detailed discussion of an example where we actually worked out each step by step without skipping any steps to discuss the situation here, and also using the simulation results in SPICE. And we have seen that the calculation and also the simulations do match very well. And also we have discussed how we can model the photodiode in this form with a very simple capacitor. Okay, if you have any questions about this example, please let me know in the comment section. I will try to answer them as soon as possible. Thanks again, and don't forget to like and share this video so that we can reach more people for this very interesting topic. Thank you very much, and see you next time.